Now let's discuss energy stored in capacitors. In fact, that truly is all that's stored in capacitors. Even if this is charged, the total charge on it is really zero. What you're doing is you're just kind of like, just like pumping water uphill so it can flow down. That's really what you're doing. When I charge this up, like so, now you'll see the light go on, but it's actually charging the capacitor, and it's getting dimmer because the capacitor is getting full. And for the voltage drop that I have, at this point now I can't put any more voltage on there, but I may be able to get that back off here just by connecting this and this. And although I lost some pressure through this light, you can see that now I'm getting, it's going back the other way, and that's how the energy is stored. And what I want to do is I want to find a relationship for the amount of energy stored on this capacitor. Okay, so let's say we have our battery hooked up to this, which is not shown, but what I'm going to do is I'm just going to put charges on here one at a time. So I'm going to put this one charge right on there, which is going to push a charge off of here and put a negative right there. Now, what was the voltage difference before I put those charges on there? It was 0. So when I had 0 charge on there, I had 0 voltage difference. So there is my first point on my graph right there. There's the first point on there. It's where the charge was 0 and the delta V across the capacitor was 0. But then I just put this charge, little tiny charge on there. So I put a little bit of charge on there, and the voltage difference, there is now a voltage difference across that. And my battery, it's still not up to the potential of my battery, so now I'm going to add another charge, and that will make this go up to right there. And another charge, and that will make that go up to right there. And keep adding charge, and that makes the voltage go up. Keep adding charge, that makes the voltage go up. And of course, charge is assumed to be a continuous amount, so it's really not happening in these jumps. It's actually going up like a constant line right there. There we go. So what I end up with, after all the charges I can put on there, I'm going to have a total charge Q. And what will be the voltage right there when I'm done charging that up to charge Q? Well, that'll be delta V total is what? Well, caps are quite overvalued, so V is equal Q over C. So to figure out the energy stored, guess what I'm going to do with this graph? Well, if you know that back to the voltage lecture, energy, the potential energy, volt U over charge, U is Q delta V, but actually be careful here. It doesn't work like that for this situation. Because my first charge, it took 0 energy to get it on. That was easy. It was free. It was no voltage difference. The next charge, I had to fight against a little bit of voltage. The next charge, I had to fight against a little bit more voltage. The only charge that I had to actually fight against the full voltage was that last positive charge, or that last electron I had to put on there. So that's why this goes up like this. So the work that I totally did by putting all those charges on there is the area under this curve. Notice that the U is not equal to Q delta V. It is not equal to that. No, it is not true, because only that very last electron that I put on there had to deal with the total delta V. In fact, the U of a capacitor, potential energy of a capacitor, just the area under this curve, it's 1/2 Q delta V. Notice it's a half because the first charge is free and it keeps getting harder to add those charges. Only the very last charge I put in there sees the full delta V that is on there at the end. So now I've got an equation for this, and we can express this in a lot of different ways. The first one I've got is the potential energy of the capacitor is 1/2 the total charge on it times the total delta V across the capacitors when I'm all done. And then let's use the fact that caps are quite overvalued. to get some equivalent expressions of this? Well, I can see I can substitute for V, delta V is equal to Q over C, and that gives me the potential energy stored by the capacitor is 1/2 Q squared over C. So there's another relationship that I can get. I can express Q as C delta V. So I can go back up here and say, okay, that's equal to, another way to express that would be 1/2 C delta V, that's Q times delta V. And notice that gives me another expression, UC equals 1/2 C delta V squared. So here are my three relationships for the potential energy stored by a capacitor. And truly that's what a capacitor is storing, is energy. And that 1/2, notice that volt U over charge does not work. It doesn't work. The potential energy of a capacitor is not Q delta V. It's 1/2 total charge Q over delta V. And again, that is because when we derive this, that first little electron we put on there had no resistance, had no delta V it had to fight against. Only that very last charge has this Q up here. Only that very last charge actually has to deal with this delta V right there. So that's why the area under the curve gives us 1/2 Q delta V. Now it should be said at this point, if this is delta V across here, if I had a free charge, like some extra free charge, like an ionized electron right here, or a positive charge right here, this free positive charge, a free one, how much potential energy would that have compared to over here? A free positive charge that is just can float through there, and it's not one of these charges because these charges cannot get off of the plate. But this one, the potential energy of this charge, the free charge, would equal Q times delta V. Because it's free, it's just going from a high voltage to a low voltage. That would be Q delta V. That is not the stored potential energy of the capacitor. I want to make that clear. That is not the stored potential energy of the capacitor. The stored potential energy of the capacitor is this. 1/2 the total charge Q times the total delta V after it's been charged all the way.